how many of you has been involved in a large modernization, legacy modernization project? Okay, so you know it's challenging. And why it's challenging? Because whenever we have to understand what the software does or why, the easiest way of doing this is to ask people who build it or use it, you know, the developers, the users, the SMEs, the business. But the problem is that in large companies and in companies at large, people come and go. And so the knowledge about what the software does and why it does is at best scattered or lost. Now, the point is, what if we could ask the source code as well, some interesting questions? And what if source code could tell us about itself too? This question is not actually a new question. There are two interesting books I really encourage you to read. One was Software Visualization, was written in 1998, was the first attempt to collect the knowledge about how to visualize statically and dynamically what the software does. And the second one is how to make this kind of visualization more agile, being able to customize them, to interact more easily, and so forth. So there is research, there are tools, but why we don't ask source code questions? I think this is connected to how we see source code. So if we ask non-dev people what code is, the thing is something like this, some gibberish that you need to be the chosen one to see through the metrics and understand what's going on. Sometimes also happens to us as developers. Now, the funny thing is that if you ask developers what do they think source code is, aside from what they can tell you, I think that as developers, mainly we see source code as literature. Huge, huge books. You have to read them through from the beginning to the bottom many times because you have to understand who the character is, who is the culprit, who killed who, and then you have to read them again. Now, if you ask the same thing to computers, they give you a slightly different answer. They tell you that source code is actually data and metadata. And there are plenty of information inside this kind of weird output. So let's see how it works. So let's take an example, the C Hello World example from the original book. As a developer, we read from top to bottom, from left to right. We understand the syntax, we guess the semantics, and we can guess that this software is about printing hello world to the console. If we switch to a computer view, first of all, the computer slices this text into lines and columns. And then if we ask the C compiler, please tell you what you see. Actually, the first thing it does is to parse this text into tokens, in lexical tokens. They are the minimum meaningful unit of text. And then produce such a gibberish output, which seems pretty damn complex, but actually if you know how to read it, it's quite easy. So first of all, you have the token, the real data. Then you have information about where is it. It's inside a file called hello.word.c, and it's line 3, starting line 3, column 1, and it ends at line 3, column 5, and from a semantic point of view, it ends at line 5, column 1. Then it tells you who is it. What's the name of this token? It's an ID, of course. And then, what does it mean? The semantic. It's a function declaration, if we take main. And also, if you look at what's next, actually, we see how to read, how we should read the next token. How those tokens are connected together is the abstract syntax tree, the syntax of the C language. Now, the interesting thing is that we can also ask the parser about this data. And it's possible to extract, actually, a data set from out of this. So we can map all those information into a table or whatever you want. So we can have the type, which is the semantic view of the token. We can have the ID, the name, and the relationship with other tokens as well, in terms of a tree. We have the information about the file, where is it, the column, the row, and the text as well. Of course, the compiler produced more output than what we need, so you see the lines with blank text. But it's pretty easy to do such a thing, even if we are not accustomed to. Now, the point is that the good news is that every programming language has a parser. Not all the parsers are good in giving you back those kind of information, but in case you have Antler. Antler is an open source library that actually is a parser, is a tool for building parsers. And these pretty small texts are the open source grammar available for Antler. There are more than 271, and you can easily build your own if you need. So there is no formal language that can't be parsed. And Antler is nice because you can ask things. So they represent the AST as a chain of objects. You can navigate through them. You can ask properties and so forth. So what is all this for? Actually, we use these kind of things pretty every day as developers. Every time we compile something, the compiler uses this metadata. But also every time we run SonarQube, we run a linter, we're actually using the AST metadata to grab interesting information, the cyclomatic complexity, the non-idiomatic code, whatever we can imagine navigating through the AST. And the IDEs as well. Every time we jump from a method to another, we are actually using these kind of things in the background. The idea is very clever nowadays to parse the source code and extract those informations. And of course, as dev as well, we are using these kind of things. We need to learn the semantic of a language. We need to know the syntax of a language in order to understand it. But the question is, can we leverage this kind of information for something else to support also the activities of non-devs? Business analysts, project manager, IT manager at large, and maybe also simplify the life of devs too. So if we look at what are the challenges of a legacy modernization project, of course the challenge is to set all those things, the known knowns, the known unknowns, and known knowns, and unknown unknowns. Now the point is that Agile helps a lot. And this talk is not about saying you don't have to do it. You have to do it. The problem with Agile is that allows us to be proactive towards the known knowns and the known unknowns. So we can collect very easily with our toolbox these kind of things. But in case of unknown knowns and unknown unknowns, we can just react to them with the Agile. We can change our plans. We can react to things that we stumble upon. Now, the idea of code as data is to actually try to be more proactive in this area as well. So anticipate problems, even the ones that we don't see at the moment. So today I want to talk about two experiences, one that has been completed, so we can also see the outcomes, and the other is still ongoing, but we think that it's worth sharing the experience and the journey so far and the learnings and so forth. So the first example is an example of addressing the unknown knowns, things that people forgot. And it's, of course, at project level. So we had actually a very specific problem. Maybe someone of you had a similar one. So we have to replace a pricing engine that was under development for the past 30 years. We went through all the standard stuff. We do the inceptions, the workshops, we talk with stakeholders, SMEs, devs, sort of. And we collect all the available knowledge that they remembered. And also the things they were not sure about and so may require further investigation, the known unknowns. And what we found out was that all the business rules were actually encoded into tables as rows, available, not available. If there is the row, means that. If there is no row, means the other thing. As instructions inside columns, you have to end this role with another or so for, and values, prices, discounts, percentage, and whatever. And the problem was that the SMEs and devs said to us, okay, don't worry, there are only 60 tables you have to care about. And when someone tells you something like this, that's the question that is spinning in your head every day. How can we tell? How can we say it's done? That's the problem. So what we did was to try to complement the usual way of working. So you do your inception, you explore the gray areas, you start a brand new conversation with the SMEs, and you refine your project and so forth with a code as data approach. And that is complementary. So the moment you collect the initial knowledge, you can start trying to see parsing source code, the legacy source code, the code that nobody wants to read from top to bottom because it's legacy, nobody knows exactly what it does and so forth, but you can parse it, trying to spot some interesting clues. Actually, in doing this, you have to be tactical. You don't want to spend too much time in doing such a thing. Otherwise, if it costs more in terms of effort than the actual project, you are doomed. So you want to get a quick and dirty result as soon as possible. You want to be pragmatic. You don't want to see the truth You just need some clues. And in our case, since the problem space was, there are tables we need to care about. So the question is there any missing table? Is there any missing procedure you forget about? And also the other problem is that they were telling us, okay, there are 60 tables to care about, but we don't know the fields. There are too many. Who knows? We have to look and see. And the key problem is that you want to build something that can be used also by BAs, by SMEs, not just by devs. Otherwise, all those interactions became more difficult. So how can we imagine, how can we actually build the pipeline in this way? I'm talking about the pipeline because it's an automated pipeline plus some manual work as well. So of course, we started with a simple thing, the list of 60 tables, and a big question mark on fields. Then we asked for the catalog of this application. The price engine was inside a huge legacy beast. And there were 1,000 tables more, okay, with 11,000 fields. Okay, this was the perimeter of the application. So there could be chances that maybe some other table was forgotten. Then we parsed the source code. The original source code was about 4 million lines of code. Of course, you can search inside the source code by table name, by field. It's an interesting exercise. You get bored very soon. So what we did was not to parse the entire thing, but to identify the entry point for the old pricing engine and resolve all the dependencies, what was needed to run the pricing engine. And this reduced the number of lines of code to 22,000. Unfortunately, out of 22,000 lines of code, there are 100,000 tokens. So we need to do something. We filter them. We merge them and we filter them. Leveraging the semantic of the tokens, we were able to identify in this very specific language when there was a hard reference to a table or a field. In this way, merging the information coming from the SME, from the DB catalog, from the source code, we were able to reduce the perimeter to 128 tables and for 5,000 tokens. Now, we had a more manageable perimeter. Of course, there were for sure false positives, so we are not saying that this is the actual perimeter. So we need to make these kind of things accessible to SMEs, BAs. And we decided to go with Excel. So we translated all those information into an Excel file that was manageable by SMEs and BAs. And this Excel file had two pretty features. We use hyperlinks inside the Excel files. And one hyperlink allowed people to, whenever they discover a table that was out of the blue, go back to the online documentation. So you need to think about those things as a way to make the feedback loop faster. But the other interesting thing was that we were able to create an hyperlink to Visual Studio Code in order to go exactly to the point in the original source code where the token belonged to. In this way, you can also see the context around the token. So you spot an interesting table that may deserve some further investigation. You can go back to the places where this actual table was referenced. Not because you want to re-implement the engine as it was, but you want to understand the context around. Actually, the solution was pretty much tactical, so we had to write just 300 lines of Clojure code. And was pragmatic because we leveraged semantic feature of the language. And by the way, most of the time, older languages are pretty much verbose. We don't like them because of this, but they are pretty much easy to be parsed for the same reason. And was accessible. It's just an Excel file. You can filter. You can build pivot tables on top of it. So you can color things out. You can add columns if you need. Okay, so was something that was, let's say, moldable, personalizable by also the SMEs and the other ones. Just a side note, why Clojure? Because I love parentheses, by the way, but that's another story. No, because, again, if you want to be tactical, you need to select the language of your choice that allows to do very simple things. First of all, being able to explore stuff. So you don't want to reinvent the wheel. So if there are libraries like Antler, you want to leverage it. If there are libraries to write access file, you have to leverage them. In our case, it was easy to use Java libraries for doing this. But we wanted also something that was very easy to build data transformation on top of it. Parsing source code around can generate a lot of metadata. You want to be fast. You want to be able to run it from your machine first. You don't need a large infrastructure to run it. So I really encourage you to explore Clojure if you don't know it. And the REPL, most of all, was the key point. So being able to explore dynamically data structures, library output, navigate the Antler tree dynamically to understand what's the best thing to extract was actually very important to be tactical. This is how it looked. Of course, it's a bit pixelized because this is actual information I can share with you exactly. So, but the idea was pretty simple. So you have a standard spreadsheet with a data set like this. As you can see in the Excel file, there were information extracted from the source code, the one that we saw at the beginning of the talk. But we also merged information extracted from the DB catalog and the SME knowledge. All those information together actually provide a good starting point for everyone. And having a link, an hyperlink for each token means that developers and BAs could go to the exact point in the source code and in the documentation. Is enhanced navigation, if you want. Instead of reading from top to bottom, you do random access to the legacy source code. It was tactical. So, what about outcomes? The original question, were actually just 60 tables? Actually, there were 40% more. Some of them were seldom used, some of them were actually edge cases, but they were needed. Of course, code as data was a complementary tool. Then we had a lot of conversation, but being able to trigger them proactively was an interesting point. But I think that the most interesting result was that we actually were able to reduce immediately, dramatically, the perimeter of the fields to just 36% of them. And this is typical in legacy modernization because over time, tables get larger and larger from column point of view. Many different kind of procedures access the same table for different purposes. So those tables were large tables, but the things that were just in the 4-hour specific business were just 36% of them. And the side benefit, as I already said to you, was that wherever there was a doubt about computation or whatever, we could also go back to exact points into the source code without being the expert neither of the language or the logic as it was implemented. So then, actually in the same customer, we were asked to think on a wider perimeter. So what about the entire modernization? This is still an ongoing activity, so I'm not able to bring you the final outcomes, but I think that even the work we've done so far can be interesting. So can we scale up code as data? And what changes if we bring it to a program level? And the use case is this. So the same application, but the entire application. So an old ERP monolithic on-prem application developed over the last 30 years. I was able to find comments saying 1987 and so forth. And you do the discoveries, you talk with people, you collect all your knowledge, and you're fine. And you can also define a target function architecture because you talking with people, you can understand what they have now, what they would like to have. You can also draw the target tech architecture because they want to move to the cloud, and also find some modernization pattern you may use based on the knowledge you acquired so far. But the problem is that the system was a huge monolithic system integrated with a lot of business processes and exchanging data, and also inside itself was a huge interconnected system. So there were two questions that are actually the questions that fly around in every modernization project. So the customer wants to know how it's going to cost or it is going to last. Usually I say 100 years. They are not happy with this answer. They want a more refined one. But the real question is where we should start from without breaking anything. Because I think that the best definition of legacy code is not if you have tests or not tests or whatever. Is that, are you scared of changing it? Why? Maybe for several reasons. So where we should start from. And I don't know about you, but when I'm asked such a thing, I feel like this guy. So where should I start from? I have to disengage a bomb and I have to find out the right kind of wire. But actually, to be more precise, I feel like this. The same guy in a dark room with people telling me what I should do. Don't worry, maybe if you cut this wire, it should be fine, and so forth. So I think this is as a consultant, this is how I feel when I have to answer such a questions. Then, okay, let's see if we can avoid panic, okay, what we can do. Actually, I have a plan, or we have a method about this. So the first thing is this. We actually collect an amazing amount of information during discoveries and so forth. This is pixelized because this is actual content. And can we translate those stickies into data? And I think this is an important question because those lines, those stickies represent complex graph of informations and also represent a way of describing the problem in a way that can be understood by people that you involved in the workshop. So you're also building a common shared language. And this can provide an interesting starting point also to ask questions to the source code as well. So if we take the normal problem and how we approach this from a program level point of view, we consolidate our knowledge, our findings, we start different tracks of project, we learn from our mistake, or if you want to be more educated by your experience, from your experience, what went well, what didn't, and you refine the scope. So how we can complement this process? Okay, first of all, if we convert at the beginning the stickies into some kind of metadata, a graph of metadata, and we try to parse the source code accordingly to this graph. We can slice and dice the source code, for example. So take the lines of code. It's a very stupid metric, but if you are able to convert the target function architecture in a series of hierarchies or whatever, and you're able to connect those things to the source code, you can start saying, okay, this part of the legacy system is bigger than the other. And you start building some KPIs. But the real game changer, in my opinion, is also the moment when you have some project of your large initiative that is going somewhere, of course, it's not going to that end, and you can collect metrics about the project. So you have replaced a component, you carved out a service, you saw how challenging it was in practice. So if you can combine those two things, so the metrics that are coming out from the project with the kind of knowledge that you acquired at the beginning and you make it as a continuous process, you can actually build interesting metrics. Let's see how we can do it. So how we can move from stickies to data visualization, if you want. And I'm representing this on a slide, but not because it's just a slide. So it's actual software we are building, by the way. So, of course, I have simplified it a bit. So imagine you can split your legacy in areas like customers or orders or whatever, and modules, so smaller functionalities inside those areas, in a way that makes sense for your customer. It doesn't need to describe exactly how the system is done, but how business people, SMEs, think about the system. The first thing you can do is try to connect, for example, your tables to your models. So how to map them, to start coloring them, and pay attention to the white boxes as well. So sometimes it's possible to connect a table to a specific functionality, a specific module, or a specific area. Sometimes not. It belongs to many. You can do the same with APIs. And by the way, I'll give you an example. When I'm talking APIs, I'm talking at large about APIs. In this scenario, we had SOAP APIs, we had RESTful APIs, we had remote procedures calls, many things. They had several applications accessing the same ERP. And by the way, the applications that were accessing the ERP were also the testimonials of failed previous tentative of modernizing the application at large. So there were character-based interface application, there were Java-based application, there were web-based application, and every time they stopped the modernization project, it was so challenging. So you can start also connecting those APIs to your target function architecture, okay? And some may map, some may not, and so forth. Then you do simple things with the source code. You can just start parsing it, and, for example, identify the things that matter the most to you. In our case, was the chain of calls, who called whom, and the access to tables, who accessed whom, read, write, and so forth. Just to give you an idea, 4 million lines of code were actually 11 gigabytes of JSON structures, all the metadata, data, and so forth. But the interesting stuff is when you connect things together. So you mapped your APIs to your target function architecture. Now inside the APIs, you may have the pointer, the entry point in your source code. And this exercise can be done also with front ends too. So you can do things in React.js and try to understand where they maps to. So it's not a problem of technology, okay? Once you map things out in the source code and you build your chain of calls, you can see, like in an X-ray, what belongs to an area and what is shared, for example, or what doesn't belong to anywhere. Remember, the white boxes are as interesting as the other ones. We actually are building such a software. So this screenshot is, of course, not very understandable by purpose because we don't want to share information. But in this case, the size of the boxes are the number of columns in a table. But we can adjust it also to express the size of the table at large, the number of rows. The point is that if you connect all those things together, you are building a large graph of connected information. And if you use the right tools, you can navigate them. And this is a game changer because you can put these on slides, but are fakes. So you get a glance of what you can do. But the real game changer, if you not only connect the information, but you use tools to navigate them. And you can navigate in whatever direction you want in this way. Now, let's see how we build the pipeline in this case. Again, it's a work in progress, but it's working. So we started as before, so we already had ways in Clojure to read everything, so we just added the stickies to the mix. Of course, it's not easy to convert the stickies to data sets. You have to think about them and the relationships, how you want to model the hierarchies and so forth, but at the end you can pretty easily get out a sort of data set, workable data set. The tables and API notation were the coloring, okay, how you can map them to. Then, okay, you get the catalogs, the DB catalogs, the API catalogs, whatever enterprise catalog you can access easily. And you can merge them together. Then you can analyze your source code. As we said, just with the same tool that we use to analyze a portion of the code, we analyze them at large, at large. And now we changed the tool. This talk is about weird languages. At large, I will tell you which is the language after. So we connected all this information we gathered from the catalogs, from the SMEs, and from the source code, and we built an in-memory graph. Now, the tool is important because building memory graph, it's easy. Navigate them is not. And changing your mind about how to navigate them is even harder. So we went for a weird option, I will tell you in a while, but the idea was that we wanted to enable exploratory navigation, also building custom visualization on top of the information that we gather. Of course, the idea is that if you can explore, you can understand what are the questions you can ask to the code. Because the key challenge here is that you need to build the right questions. So you have the business questions at the beginning. So how much is going to cost, where I should start from. You have to translate those questions in question you can ask the source code to. And once you are able to extract those information, they may be lines of code split by modules, they may be whatever you want. You can then get back this information to Excel or whatever other tool you want and try to contribute with evidence, not just gut feeling, to the roadmap or refining the roadmap. Because the point is that whenever we rely on experience or gut feeling, which is absolutely nice because people are amazing in making predictions, of course, our roadmaps need to be validated by the actual work on the ground, and this has an impact on cost. As a consultant, we like to have long-running projects. Customers are a bit more hesitant in having such a thing. So, was strategical? Yes, because we were able to merge the stickies with source code, so slice and dice the legacy code base from a point of view of a target architecture. Comprehensive, yes, because you can easily extend and integrate many, many sources. You need to build the right kind of abstraction, of course. Okay? You don't care about the language. You care about the things inside the source code you matter the most to you. And need to be flexible. In this case, we didn't want to have something that was commonly used, but something that was flexible enough to change our minds about how to visualize them. So what we use Faro for doing this, which is another weird language. You know, I fancy this kind of 30, 50 plus years old language. It is a modern Smalltalk. The really interesting thing is that there is a large community of researchers around Faro that actually build tools to represent whatever else language you want to explore. In Smalltalk, historically, these kind of things were actually normal. So you have plenty of tools to understand how the software inside the virtual machine of Smalltalk is doing, what the properties, and so forth. So the interesting thing, they applied the same kind of tools to analyze other software, Java project, C++ project, and so forth. So there is a library called Russell, which is like 3D GS, but for software development. And it allows you to build very easily very complex graph views or whatever you want. And the interesting stuff is that this library is integrated with what is called the inspector inside Smalltalk. So in Smalltalk, you can inspect whatever object is in memory, see the attributes, navigate the connection with other objects, and so forth. And the interesting stuff is that you can do it textually, so you can see text of the properties, or you can do it graphically. So the integration with Russell is very important. And the other point is that you can pause and resume. Smalltalk invented the VM from a certain point of view. So no matter how complex it is to load your graph in memory, you can just save everything. The objects, the views that you are using, just a snapshot, you save to disk, and you start from the same point of view. This allowed a lot of exploration. We are still building it. It's very easy. The real challenge is not building the visualization, is understanding what is the best visualization for our scope. That's the game changer. So if you spend too much time trying to understand how to build the actual code to visualize stuff, you're on a dead end. What we learned so far? Do we have the answer? Not yet, but we are getting empirical and factual evidences about it, how it's going to cost and how it's going and where we start from. The learnings are three. First of all, look for what doesn't match, the white boxes. These are probably the unknown unknowns. And if you spot them, you can uncover unseen risks. Maybe it's about shared resources, maybe it's about processes that nobody remembered about. My guess in this project is that there are a lot of batches running that are uncharted. So look for white spaces, things that doesn't match. And you can do it incrementally. Of course, building all those kind of stickies and data, it's an iterative project, so a problem. So the second learning is look for what overlaps. Whenever there is a table, a procedure that actually is shared by different modules, now we can tell this. That's important. So if you bring in the perspective of the target function architecture, the way you want to split the monolith, the way you want to build your new services, you can see how many of those paths are actually intermingled. And these are potential issues from a modernization patterns point of view, from mitigation, and so forth. The third point, which is the most controversial in my opinion, but we need to be pragmatical as well, is to look for what matches. Because, yes, for example, line of code. What lines of code can tell us about a legacy system? Of course, in a legacy system, the problem of a legacy system is that you probably was not able to delete stuff that you don't need anymore. That's the problem, of course. So lines of code doesn't tell the entire truth. But if you compare them, if you split the code by the target architecture, if you start comparing them, they can tell you something interesting. If something is tenfold another one, there is a potential problem. Okay, so we need to be pragmatic about what matches and try to get as much as we can out of them. I'm slightly out of time. I just want to finish with a couple of things. So one is a sentence from the software visualization. We are spending a lot of resources in visualizing how the software has to be built before doing it. We are not, as an industry, in my opinion, very well accustomed to monitor graphically what the software, how the software is built actually, and what it does statically and on runtime. And this is a game changer again, in my opinion, because this is one of the best practices, if you want, to avoid going to a new legacy. If you start monitoring after you have built the software itself, you can monitor how it evolves over time. And documentation is always challenging. Human-based documentation is challenging. There are many, many things you can extract from software itself. The second point, from the second sentence from the same book, is about you need to care about how easy it is to change your mind on data visualization. If it costs too much, it doesn't work. So there is a very interesting concept that has been brought by the Faro community, which is about moldable development or moldable data analysis. Using Faro, for example, you don't have to build the application, the dashboard. You just have to tell to each object how they want to be represented graphically. And the inspector is able to navigate through them. So make it easy. You can build, of course, I've been building dashboards about source code for a while. They're fine, but I think that this is absolutely to a different level. There are examples, there are many things, and so forth. And that's all.